picture this. It's 2 in the morning. You're staring at your monitor. Your eyes are just totally bloodshot. And you're trying to debug a lock-free data structure that is inexplicably failing in production.
Oh, yeah. The absolute worst.
Right. You're reading the code over and over. The logic looks flawless. I mean, mathematically, it should work, but it doesn't. Your threads are colliding, data is getting corrupted, and just nothing makes sense.
It really is the ultimate nightmare for a systems engineer. Because, well, at that point, you aren't fighting your own logic anymore.
No.
You're fighting the compiler, the operating system, and literally the physical silicon on your motherboard. You're fighting decades of architectural decisions that you can't even see.
Exactly.
Yeah.
Which is why you can't just stare at the syntax to fix that bug.
Yeah.
To actually understand why your code is failing, you have to understand why the primitives you're using were built in the first place. So today, we're taking a deep dive into the historical evolution of lock-free data structures in C++. Specifically, we're looking at the standard atomic flag and how memory models evolved from the sort of Wild West of C++ 98 all the way up to C++ 23.
It's quite a journey.
It is. And we really need to answer the core question today. Why does standard atomic work this way, and what constraints actually define it today?
Right, and to really get to the bottom of that, we have to rewind. We have to go back to a time when C++ existed in a state that researchers, very politely, I might add, refer to as concurrency ignorance.
Concurrency ignorance. I love that term.
Yeah, it's accurate. Back in the C++ 98 and C++ 03 eras, the standard literally contained no mention of multiple threads of execution. None.
Yeah, none at all.
Zero. No memory barriers, no atomic operations. The language specification basically just assumed a purely single-threaded universe.
Okay, so if you were building a high-performance server back then, which people obviously were, how are you actually doing multi-threading?
Well, you were treating it as an entirely external problem.
Oh, like just handing it off to the OS.
Exactly. You'd use an operating system library, like Threads on Unix or the Win32 API on Windows. The prevailing fallacy was just that concurrency was an external library's job. But treating threads that way in C++ was fundamentally broken.
And why is that?
It comes down to aggressive optimizing compilers.
Okay, wait, I need to stop you there. Why does the compiler care if I'm using an external library for my threads? Doesn't it just, compile the code I wrote?
It compiles it, yeah, but it also transforms it. A late 90s compiler assumed it was operating in a vacuum. Its only job was to make your single thread run as fast as humanly possible.
Right.
So it felt entirely free to reorder instructions or eliminate redundant loads. Like, let's say you have a loop, and inside that loop, you check a shared variable.
Yeah.
The compiler looks at that and says, well, nothing inside this loop actually modifies this variable, so I'm just going to read it once before the loop starts and use that cached value to save time.
Okay, let's unpack this real quick. Treating multi-threading as an external library in C++ 98 is like adding traffic lights to a city where the cars, meaning the compilers, don't even know what a road is.
That is a great way to put it.
They just teleport around to save time. Moving a read operation outside of a critical section might perfectly maintain the illusion of sequential execution in one thread, but if another thread is actively updating that variable.
Your first thread is completely blind to it. It's now permanently stuck reading a stale, cached value.
Wow.
Yeah, that teleporting analogy is spot on. And this wasn't just some, theoretical annoyance. It was actively breaking real software. Hans-J. Boehm published a pivotal paper in 2011 titled How to Miscompile Programs with Benign Data Races.
Benign data races. People really thought those were a thing.
They did. Back then, engineers honestly believed in them. They thought, oh, I'm just doing a double-checked lock for lazy initialization. It's totally fine if there's a tiny race condition.
And Boehm's paper essentially said, no, you're playing with fire.
He proved mathematically that at the source code level, almost no data race is truly benign. Because the moment the compiler spots a race, even a seemingly harmless one, its single-threaded optimization rules just completely destroy your logic.
Because it assumes the race can't happen.
Exactly. It might optimize away a secondary check, assuming nothing could have asynchronously changed the state. Suddenly, your program is trapped in an infinite loop, or worse, it's operating on uninitialized garbage data.
And to make matters worse, while the compilers were teleporting your code around, the physical hardware was doing the exact same thing, right?
Oh, absolutely.
Because you had the x86 architecture, which uses total store ordering, or TSO, and that's a relatively strong memory model. It guarantees that scores from a single processor are seen by the rest of the system in the order they were issued.
Right. By-86 was relatively sane.
But then you look at architectures like ARMv7 or PowerPC, and they use weak memory models.
Yeah.
They reorder things at the silicon level constantly just to keep their execution pipelines full.
But the absolute extreme end of that spectrum, the architecture that truly terrified the Standards Committee, was the DEC Alpha processor.
Oh man, the DEC Alpha.
Yeah, it had a memory model so wrecked that it could literally reorder two dependent loads.
Meaning what, practically?
Yeah.
Like it could load data from an address before it even knew what the address was.
Mechanically, yes.
That is insane.
It heavily utilized speculative execution and aggressive caching. If it had to read a pointer and then read the data that pointer pointed to, the alpha might speculatively use the cached value for the target data before the pointer load even finished.
Wow.
It became known as the Alpha Anomaly.
That sounds like a literal causal paradox.
It creates them. This led directly to this mind-bending academic problem that researchers like Mark Batty and Victor Fafaides had to solve. It was called the out-of-thin-air problem, or OOTA.
Okay, lay this out for me.
Imagine thread 1 speculatively assumes a condition is true, so it writes the value 42 to variable x.
Tracking so far.
Thread 2 sees x as 42, and because of that, writes 42 to variable y. Then thread 1 finally checks variable y, sees 42, and uses that to justify its original speculative write to x.
Wait, what? So they both started 0,
Yeah.
but because of aggressive hardware speculation, they both just magically become 42.
Yep.
The values circularly justify their own existence.
They literally come out of thin air. So moving into the late 2000s, the C++ Standard Committee realized they had to build a completely new formal foundation.
I mean, they had to.
They had to draw a hard line. All data races had to be declared undefined behavior. They had to mathematically forbid these out-of-thin-air results, but without accidentally banning the standard safe compiler optimizations that make C++ fast.
Which is a massive tightrope walk.
Yeah.
And that brings us to the actual construction of this foundation in C++11, and they had this huge architectural choice to make right out of the gate.
They did. Proposal N2145 suggested a fence-based model.
Done.
Yeah, in this approach, concurrency is managed by inserting global barriers or fences into your code to synchronize memory across threads. But they ultimately rejected that in favor of proposal N2427, which codified atomic types.
Right, so instead of a developer trying to manually scatter these global stop signs throughout their code, the atomic property is bound strictly to the data type itself.
Exactly.
If you try to access it normally, the compiler automatically enforces the synchronization protocol. And the absolute baseline primitive they introduced to anchor this whole system was the standard atomic flag.
Standard atomic flag was designed to be the ultimate lowest common denominator. It was the only type strictly mandated by the standard to be lock-free on absolutely every hardware platform.
Meaning no hidden locks anywhere.
Right. Because if you use a standard atomic integer and your specific obscure hardware can't support atomic math, the compiler is allowed to quietly inject a hidden mutex to make it work. But the standard atomic flag, guaranteed to be purely lock-free metal everywhere.
But the real heavy lifting in C++11 wasn't just the types, right? It was the memory model backing them. They adopted the data race-free implies sequential consistency model, or DRF-SC.
Which basically means if you use your atomics correctly to avoid data races, the system will behave sequentially.
Like a normal program.
Right, as if all thread operations were just interleaved on a single processor with none of that mind-bending reordering. But enforcing sequential consistency on every single operation is incredibly slow because it just flushes hardware pipelines.
So to let developers tune performance, they introduced the 6 tiers of memory ordering.
The standard memory order enumeration.
Yeah. You have relaxed, which offers no synchronization, just atomicity. Then consume, which we are definitely going to dissect in a minute.
Oh, we will.
Acquire, to prevent subsequent reads from moving up before the atomic operation. Release, to prevent previous writes from moving down past it. Accrual, which combines them. And sixth, the default, which provides that total, heavy, global ordering.
This created a rigorous mathematical framework defining what happens before and synchronizes with actually mean. Synchronizes with isn't just some vague concept anymore. It is a literal mathematical edge in a dependency graph.
How so?
Well, say thread A performs a release store, and thread B performs an acquire load on that same variable. That creates a strict edge. Everything before the store in thread A is now guaranteed to be visible to everything after the load in thread B.
That's incredibly powerful.
It was so formal that Bartosz Milewski actually used it to mathematically prove the correctness of the Peterson-Lock algorithm under the new standard.
But giving developers this massive theoretical toolkit in C++11 immediately revealed a huge disconnect between academic math and actual silicon,
It really did.
which is exactly what happened during the C++14 and 17 eras. They had to step back and refine the wording around those out-of-thin-air results in C++14 because defining what constitutes a real dependency versus a fake speculative one in the math was just incredibly slippery.
And by C++17, that disconnect basically hit a brick wall. A major feature from C++11's standard memory order consume was officially discouraged. This is actually one of the most instructive failures in the history of systems programming.
Okay, so what exactly was Consume supposed to do? I know it was championed by Pauline McKenney, specifically to support RCU, or Read Copy Update, in the Linux kernel.
Right, and RCU is critical for Linux performance. The idea behind Consume was to exploit a natural hardware feature on chips like ARM and PowerPC. If you load a pointer, and then your very next operation depends on the value of that pointer, like dereferencing it, the physical hardware naturally guarantees those two things won't be reordered.
Because it can't.
Exactly. The hardware literally cannot fetch the data until it knows the address. So McKenney argued, why issue a heavy acquire memory barrier when the hardware naturally enforces the ordering through the data dependency?
In theory, that is brilliant. You just get synchronization for free.
In theory. But there was a massive technical constraint in the compiler architecture. To make Consume work, the compiler had to mathematically track those specific data dependencies across all of its intermediate optimization passes.
And compilers are expressly designed to break and simplify dependencies to make code faster.
Exactly.
Right? I was actually looking at a great example in the sources. Imagine you write x equals data bracket r minus r. Mathematically, r minus r is just 0.
Simple algebra.
So the compiler's algebraic optimization pass sees that and simply rewrites it as x equals data 0. The dependency on the variable r completely vanishes from the compiler's internal representation.
Exactly. But if R was loaded using a consume operation, the compiler was legally required to preserve that hardware-level ordering guarantee. Once the optimization pass erased R from the equation, the compiler essentially forgot that the dependency existed.
Oh no.
Yeah, and it would freely reorder the subsequent loads, completely destroying the synchronization and breaking the code.
So how did compiler developers actually fix it? Did they rewrite their optimization engines to track these brittle dependencies?
No, they realized it was practically impossible. Teaching every single optimization pass to preserve these delicate dependency chains was overwhelmingly complex. So compiler developers simply gave up.
They gave up?
Pretty much.
Yeah.
Every major compiler essentially implemented standard memory order consume by silently promoting it to standard memory order acquire.
Wait, they took a highly tuned zero-cost optimization and just aliased it to the slower, heavier hardware barrier it was supposed to replace.
Yes, they did. The trade-off was just too harsh. You can't ask a compiler to be aggressively fast and meticulously careful about vanishing algebraic dependencies at the exact same time.
That perfectly highlights how fragile this ecosystem is. So C++17 admits defeat on consume, but then we hit C++20, which the sources call the Great Expansion.
A very fitting name.
Because up until this point, we've only been talking about reading and writing memory. But C++20 moves from passive storage to active coordination.
And rightfully so. I mean, before C++20, if you wanted a thread to wait for an atomic variable to change state, you basically had to write a spin lock. Your thread literally just sat there in a tight while loop, checking the value over and over millions of times a second.
Which means it never yields to the operating system scheduler. It just burns an entire CPU core at 100% capacity, waiting for a Boolean to flip.
Yeah.
That's terrible for system performance, not to mention battery life.
It's awful. But proposals P1135R0 and P1135R3 completely changed the game. They added the wait, notify one, and notify all methods directly to atomic types.
So no more spin locks.
Right. Now, instead of spinning, your thread could efficiently yield its context back to the OS, go to sleep, and let the kernel wake it up using highly efficient underlying mechanisms like the Linux futex.
And C++20 didn't stop there either. We finally got atomic floating point operations, which the scientific computing and GPU communities desperately needed for their high-performance reduction algorithms.
Oh, yeah. That was a long time coming.
And we got standard atomic graph from proposal P1643R MATI 0.
Atomic graph is huge. It allows you to perform atomic operations on non-atomic variables.
Why is that so important?
Well, if you have a massive array of standard integers, you couldn't always afford the memory overhead of making every single element a dedicated standard atomic type. Atomicref lets you dynamically enforce atomicity on a standard variable only when you actually need it.
Okay, so C++20 is this massive leap forward. But then we get to C++23. In proposal P0995R1 added the test method to the standard atomic flag.
Yes, it did.
Hold on. Atomic flag was introduced way back in C++11. Are you telling me that from C++11 all the way to C++23, it didn't have a test method? You had test stand set to modify it and clear to reset it. How did you just read its current state without changing it?
You couldn't.
Are you kidding me? For 12 years, you literally couldn't look at the flag without altering it.
It is a classic example of how strict architectural minimalism can totally backfire. Remember, they wanted Atomic Flag to be guaranteed lock-free on the absolute weakest, most obscure hardware out there.
Right.
Some ancient hardware only supported destructive read-modify-write instructions. So, the committee provided only those destructive operations. By doing that, they made Atomic Flag practically useless for basic, non-destructive polling.
This is wild.
It took over a decade for C++23 to finally correct course and admit that, hey, modern developers just need to be able to read the flag.
That is staggering. It really emphasizes the constraints these designers were operating under. Speaking of constraints, we talked about consume failing. What other tools got thrown out because they didn't fit the architectural reality? I know people used to use the volatile keyword for threading in older C code.
They did, yeah, but it was a massive misuse of the tool. Volatile was designed strictly for memory-mapped I/O, like reading data straight from a hardware sensor.
So what does it actually do?
It simply tells the compiler, don't cache this value in a register, fetch it from RAM every single time. But it does absolutely nothing to ensure atomicity across CPU cores, and crucially, it doesn't emit the hardware memory barriers needed to prevent reordering. The committee rightfully rejected it for thread synchronization.
They also rejected the Transactional Memory Technical Specification, the TMTS. This is the idea where you could just wrap a chunk of code in an atomic block, and it would execute atomically, automatically rolling back if there was a conflict with another thread.
Sounds great on paper.
Sounds like magic. Why didn't we get that?
Because it violated the core C++ philosophy of zero overhead abstractions. To make transactional memory work, you either need a massive, heavy software runtime to track all the memory states and manage rollbacks, or you rely on hardware extensions.
And the hardware wasn't there.
The early hardware extensions, like the Intel TSX instructions, proved incredibly buggy and unreliable. The atomic types we have today won because they map cleanly, predictably, and directly to single CTAL instructions without a hidden runtime.
Which highlights this incredible hardware symbiosis. The C++ standard didn't just adapt to hardware, it actually started dictating it.
Yes.
For example, ARMv8 introduced entirely new hardware instructions, LDRR for load acquire and STLR for store release. They built those explicitly so they could map perfectly to the C++ memory ordering semantics we've been talking about.
But this raises an important question, and it's deeply ironic. If modern C++ memory models are perfectly synchronized with modern hardware, like ARMv8, what about the DEC Alpha, the architecture that caused so much panic with its incredibly weak memory model and its out-of-thin-air anomalies?
Right, the processor that could load data before it knew the address. Where does it fit into the modern standard?
It doesn't. The DEC Alpha is a dead architecture. It hasn't been commercially relevant for over 2 decades. Yet the fear of the Alpha Anomaly heavily influenced the complex, paranoid drafting of the original C++11 memory model.
You're kidding.
No. The committee essentially hard-coded the ghost of a dead architecture into the foundation of modern C++.
Wow. Every time a developer wrestles with the mathematical complexities of the C++ memory model today, they are literally carrying the baggage of a dead processor from the 90s. That is wild.
It is. But that brings us to where we are today. The conversation has shifted. We aren't really debating how to implement these low-level primitives anymore. The focus now is on how to verify them and keep them safe.
Because formal verification is huge now. The sources highlight the rise of academic tools like HERD and CleepyMem. You can write these tiny concurrent litmus tests, and the tool will mathematically analyze how your code behaves against the formal C++ memory model.
And what those verification tools have revealed is that the C++ model is constantly under fire from both sides.
How so?
Well, academics argue it is too weak because the out-of-thin-air problem still technically lurks in the theoretical margins of the specification. But compiler writers argue it is too strong because the strict barriers forbid certain optimizations that would actually be perfectly safe and highly performant in practice.
It's an impossible balancing act, and it perfectly frames the biggest debate happening in the ecosystem right now, the future of memory safety. We're seeing major pushes like the Safe C++ proposal that want to create a subset of the language where data races and memory corruption are fundamentally impossible to even compile.
But that creates immense tension. Lock-free data structures, the very things that power high-frequency trading platforms and game engines, inherently require low-level, dangerous memory
You
manipulation.
need that access.
Exactly. If you enforce absolute safety by taking away those raw pointers and relaxed atomics, you lose the ability to write the high-performance infrastructure that makes C++ valuable in the first place.
Which is exactly why Bjarne Stroustrup and others are advocating for profiles. Rather than locking down the whole language, profiles allow a team to opt in to safety guarantees. It's kind of like engineering a supercar that is mathematically impossible to crash, but still giving the professional driver a physical switch to turn off traction control when they absolutely need peak track performance.
That is the perfect way to look at it. You enforce the safety net for 99% of your application code, but you preserve access to the raw metal for that critical 1% of infrastructure code.
Okay, let's synthesize all of this.
Mm.
For the professional engineer listening to this right now, the one staring at that broken lock-free code at 2 a.m., what is the ultimate takeaway from this history?
The ultimate lesson is that concurrency cannot just be treated as an API. It represents a strict, incredibly complex contract between the programming language, the compiler optimization passes, and the physical silicon.
It's all connected.
Deeply. When you type standard memory order acquire, you aren't just calling a function. You are generating specific hardware instructions and erecting compiler barriers that were shaped by decades of trial, error, academic debate, and the failure of ideas like consume and transactional memory. You have to design your concurrent systems respecting those architectural constraints, because you cannot outsmart the compiler's optimization rules.
You are standing on the shoulders of developers who literally fought the compiler teleporting their code and hardware architectures that pulled data out of thin air.
Precisely. And as we look toward a future of entirely new hardware architectures, maybe quantum computers with entangled